Okay, so for this chapter, we'll talk about data imports, and for the learning objectives include reading data from disk. We'll use the read function, the read R package, and using the read functions and family of functions. We'll compare and contrast the read underscore, okay, so a bunch of read functions with the base R equivalents. And we'll also pass character data in other types using the read R function, which is the different functions of the pass function. And in that, we list the complication that arise when passing numeric strings. We'll understand how various character encodings can make it tricky to pass characters. We'll also diagnose the problems that arise when we use the read R functions, and we'll write data into disk using the write function, which is a family of functions as well. So let me start. To read the plain text rectangular files into R, we will learn principles which will be applied into other forms of data. So we'll first load the tidyverse package to get the read R package, which is part of the core tidyverse, the tidyverse package. So I saw this function package. So you suppress the package startup messages, and I just have a question if there's any harm in loading tidyverse as such. What I understand is with this, it doesn't print out the package and their function and their versions. Sorry.
So yeah, it's, the only reason not to do that is to, like, getting the conflict messages can be helpful if something goes wrong. But other than that, yeah, you don't need to get that notice every time.
Okay. All right. Thank you. Yeah. So these are the different functions that we'll use. The read CSV will read the comma delimited files. There is the read CSV2 read underscore CSV2. It reads semicolon separated files. And this is common in countries where we have comma is used in place of the decimal place. And there's the read underscore TSV file, which reads the tab delimited files. And finally, the read underscore delim, which reads in files with any delimiter. There's another function that is read underscore FWF, which reads files with fixed width. And in this function, we have got to specify the widths we have to specify the width, and also we have to specify the positions with this function. The FWF position. So there is also another function of read underscore table, which reads common variation of fixed width files where columns are separated by a white space. We have another function called the read underscore log. This reads the Apache, I hope I'm pronouncing it correctly, style log files. And as suggested, we are to check out the WebReader R, which is built on the read underscore log, and it provides helpful tools. But in this chapter, we'll focus only on read underscore the CSV file.
Lucy, may I ask a question?
Yes.
I didn't quite get the read underscore FWF. So what does fixed width mean? And can you give an example maybe as to why you would have a file that is fixed width and what positions you need to specify?
Okay, so I'll explain. I'll answer parts of your question. From what I understood from chapter 10 is width is about columns. That is what I understood, that width is the same as columns, because there's part of the exercise where we are asked how do we want to specify the number of columns using in this function, the read underscore FWF.
So I threw something in the chat to kind of show it, although I think I might have missed a space now that I'm looking at it. The idea is where it's like you're visually making something that makes sense in the text file where you line all the characters up. That's what makes it fixed width. So it would be like column 1 is 3 characters, or I guess in my case, it's 5 characters wide or 6 characters wide. And there's always the first 6 characters are column 1, and then the next, however many I break it up as. So I am counting the spaces as part of the character. So this space is column 1, that space is column 2, and then another space is the column 3. And you would tell it, this is my breakdown, that it's my first column is 6 spaces wide, 6 characters wide. Second column is 8 characters wide, 7 characters wide, whatever. And so that's where you're telling it exactly. And so if if you tried to run that and you had something like that, and you say, okay, my first column is 8 characters wide, then it would be that. So that would be what it puts into the first column, because it's just taking the first 8 characters and saying that's column 1, whatever is there. I don't I almost never, I can't think of any time in recent history that I've worked with a fixed width file.
Right. Yeah, I was just wondering what kind of data would show up that way, or why would you want it that way?
I think the most likely case would be if someone made a text file to be human readable, and then you were trying to read that in. So they spaced it out to be pretty when you're looking at it. Okay. And then when you try to read that in, but then often the way they're spacing it out would have spaces, or you could use something else as your delimiter. But if it has all those extra spaces, that can be a pain to deal with. But if it's fixed width, it'll deal with it.
Got it. Okay, that's interesting. Thank you, Lucy.
Okay, thank you, John.
You're welcome.
So there's a note here that not only are CSV most common forms of data storage, but once we understand how to use the read underscore CSV, we can easily apply the learned knowledge to all other functions stated above. So the first argument in this function is the path, which is the path to the file to read. So I downloaded the Penguin CSV file and I read it, and this is the path where it is. So the read CSV prints out a column specific that gives the name and the type of column, as we see above here. So it gives the columns and the type. You see, this is the column and length underscore m, the millimeter is double, and so on. So this is important part of read R, and we will see more about this later. We also supply an inline, we can also supply an inline CSV, and this is useful in experimenting with read R and also creating reproducible examples to share with others. So this is how we do if you want to create a table object from using the read underscore CSV. So the first row here is by default used as the column names, and the other rows that we have here, the lines rather where we have got the values, these are the rows that will be contained in those columns, and we separate the columns using a comma. So like I've said, this is the common convection where we have the data is as the column names. So sometimes we want to skip a few lines of the metadata at the top of the file. So we can either use argument skip is equals to n to skip the first n lines, or you can comment it using the argument comment is equals to any character that you put that you want to comment. So for this case, we put hash to drop all lines that start with that. So we have, this is the first line of metadata, this is the second line of metadata, but then I want to skip these first 2 lines. So I'll say skip is equals to 2. And you see it returns a table object with only the XYZ columns. The other option you've said is to put a like a character here. So here I've put hash in. This is, I want to skip this, and I'll use the argument comment is equals to this hash. So it will return, it will print out a table object with 1 times 3 columns as expected. Perhaps the data doesn't have column names. So what do? We use the column underscore names is equals to false to tell CSV to not treat the first row as the headings. And you've seen that by default, it does that. So instead, it will label them sequentially from X1 to Xn. So this is the case. And we see here this, we have been introduced to something new here. So this is backslash, yes, backslash and small n. This we're telling R to skip, to add a new line, sorry. So this is the note. We can alternatively use the column is equal and call underscore names arguments, which is a character vector used in column names. So we have got, these are the values that we want to contain in our CSV file, and we want our first column to be called X, a second column to be called Y, and our third column to be called Z. Okay, so we have another option that commonly needs tweaking, which is when we have unknown data. So we can use NA to, so instead, as we print it out, we'll have, it will be the unknown value represented with NA. And you can see here that we see NA is equals to dots. Yeah, enclosed it in this quotes. Sorry, I was looking for that one. So you can either use to, apart from the dots, you can do also a space. I tried that as well. So what we have learned above, we can apply it in the read underscore TSV, and also those with fixed files, the read underscore FWF. Please note that to read more challenging files, we'll need to learn more about the read R passes, each column, turning them into R vectors. John, would you please explain that?
So each column in a data frame is a vector. And so, okay, like let's say, let's say you had a column or had data where the data has both like commas and semicolons within each column. That would be an example where you have to know a little bit more in order to read that in, because you can't use read CSV, you can't use read CSV2. You would probably have to use read delim and tell it how that file happens to store its data. Sometimes maybe it uses a pipe character or whatever, and so you have to use the more advanced things in those cases. I'll say, like, it depends what you're working with, but read CSV is going to work a lot of the time. Like, a lot of data is in CSV format. So okay. Often start there, and then if it doesn't work, go from there.
Okay, thank you. So let's compare the functions, the read underscore CSV with the base function, the read.csv. So there are 3 reasons as to why the read underscore CSV is better. First is that they are quite fast. That is almost 10 times their base equivalents. So this stated that the long-running jobs have a progress bar, hence we can see what is happening. And also we can look at speed from the data.table function, the data.table package, the fread function. So it doesn't, okay. doesn't fit quite well into the tidyverse, but it can be a bit fast. So the second reason is that it produces tables. That is, as we learned, that it doesn't convert the character vectors to factors, that it doesn't change the data type. It also uses the row names and manipulate column names. It adds a data type below the column name. They're also more reproducible. If we use the base R functions, they do inherit some behaviors from our operating systems and environment variables. So the importing code onto our computer may not work into someone else. The other section is passing a vector. We learn about different pass underscore functions that take the character vector and returns a more specialized vector, such as a logical integer or a date. So here, if we look at, we have got true, false, and NA. If we pass this function underscore logic, the pass underscore logic, and we look at the structure, we see that it returns, it gives us a logic, and it returns the values. Yeah, we can also see the same for the pass underscore integer. So it returns integer, as you see, int. Also for the date, it returns dates. So not only are these pass functions useful in their own, but they're also an important building block for readr. So like any other, all other functions of tidyverse, these pass underscore functions are uniform. That is, the first argument is a character vector to pass, and the NA argument, it specifies strings which should be treated as missing. In the example here, we want everything to be returned as an integer, but we have an unknown value, which is represented with a dot when you're entering the data. So as we're printing out, we'll see that we'll have NA. So suppose this passing fails, a warning will then be returned. So in this case, we want to pass integer. However, we have the ABC and we have a decimal. This is so 123.45, the decimal. So we'll see some warning that two passing did fail. And the failures will be printed out. So we can print out the failures and see. So it tells us row 3 and 4. Okay, we have this. It returns a table of two rows because two passing did fail, and 4 columns with the following. So it tells us the row, the column, what was expected, and the actual. Okay, so when you have many passing failures, it's best to check what is the problem using the problems function to get the complete set. This will print out a table that we can manipulate it using a dplyr. Okay, I realize there's so many chats I haven't. Okay.
I think you're caught up with what we've been talking about in the chat.
Okay. Okay, so for us to use the passes, we need to understand what is available and how to deal with the different inputs. So there are 8 important passes function. That is one for logical and integer, and this will pass logicals and integer. So for double is strictly meant for passing numeric, but when we have pass underscore number is a flexible numeric. So it means that here what I understood is that if a number has like another character or some wording before that number, it will still return it. It will still return it as an output with only number, in discarding any other thing that is around it. So it's not worth to note that these are more complicated than what we might expect due to the different part of the world, how we write numbers. So we'll see in the next section. The other function is pass underscore character, and this will pass a character. So what this is happening, what this is doing is the character encoding, and this makes it complicated, unlike how simple it should be, as we expect, as we think, sorry. The other thing is pass underscore factor, and this creates factors. So factors are data structures that R uses to represent categorical variables with fixed and known values. So for dates and time, we have the following functions, the one with underscore date time, one with underscore dates, and the other one with underscore time. We'll see how the following are applied. So these are the most complicated because of the different ways we write dates. Okay, so for numbers, the three problems that...
Sorry,
sorry.
Federica was looking for more info about problems. It's really funny because I've used Reader a million times, and I'm sure I've used the parse functions at some point, but I had forgotten they exist. And problems, I totally had, like, if I've ever seen it, I didn't remember it. And so I love that about this book. That's something that I'm like, oh, I can just skim this chapter. I know all this stuff. And then I start looking at it, I'm like, oh, whoa, I actually don't think I actually knew that. And problems is great. I would guess that would still be available if you used Reader, since Reader is using the parse functions if you used read CSV, it's using the parse functions under the hood. And so you could probably run problems on something that you read in using read CSV. And it generates this tibble that tells you row by row, this was screwed up because of this thing. We expected an integer and we actually had ABC, so it comes in as NA. But I think it's a nice one to know about and to pay attention, like to remember that it exists, because sometimes it is, you'll try to read something in and you'll get an error and you're like, oh, okay, somewhere in my 10,000 rows, there was something that was weird, and you're trying to figure out exactly what it was. And problems just tells you it was here. This is what I saw. This is what I did to it. And it's not what I was expecting. And the reason that this is super important is that things like read CSV are guessing which parse functions to use. And sometimes they guess wrong. Like sometimes the first 10 rows of your data are integers, or however many it uses, 100 rows, I'm not sure. And so it's like, oh, this must be an integer column. But then it gets past that and there's decimal points. And so you would have all these numbers that don't get parsed properly, and problems will tell you, these are the ones that didn't parse properly, and here's what I saw and what I got. And then that can help you debug things. It's 1,000 rows. Okay. But yeah, if you have a 10,000 row file and the first 1,000 is all integers, just happens to be, and then number 1,001 is 1.2, it'll parse that as NA because it's like, well, that's not an integer. I don't know what to do. And so, yeah.
Okay, thank you so much.
Thank you.
At the moment, we'll now study the numbers. So for numbers, we'll expect three different problems. And the first problem is because of how numbers are written in different parts of the world. Like you've said, that some countries will use decimal in between the integer and a fraction, but as others use a comma. Also, numbers are often surrounded by other characters that provide some context, such as currency, as we have $100, and also percentage. The third thing is that numbers are frequently contained in grouping characters to make them easy to read. So we have, like, this is 1,000,000, and the grouping character varies differently. So to address the first problem, where the numbers are different, they're written in differently in other parts of the world, we'll use the argument local that is an object that specifies the passing options, which differs from place to place. So here this is the most important option, is the character that is used as a decimal mark when passing numbers. And also we can override the default value of the dots by creating a new local, I hope I'm pronouncing it correctly, setting the decimal mark arguments.
This is very interesting. Very interesting. Just because this has happened recently to me, to find a CSV with a column of numbers, like sort of number of percentage of deaths and everything. So they were divided by age classes, and there were some with dots and some with commas. So you actually there was a bit of confusion when you made the formula. This was in Excel. So when you actually made the formula, you find out that you have a certain number of nav values, and then when you go and checking the column for understanding the reason, you find that you have two different like codification of numbers. So they're not decimals, they're not millions. So what are they? So maybe with problems, I can see this. Can I? Or using this function?
Within one column, that's still going to be hard. Like if you're going back and forth between period and comma, because you would be telling it that this one uses periods or this one uses commas. And if it's both, then you gotta, you'll have more work to do. I think you're trying to say something, Ryan. You're muted.
No, sorry about that. No, I was thinking in the top of my head, listening to Frederica or talking about the mixed values or mixed syntax within one column. You would need another stage of wrangling that would separate those two, right? You would want to take association to, okay, this is going to be using commas, this is going to be using periods, and then between the two of them, yeah, that would be a really funny mixed logic. The reason that I think this could be a possibility, so let's say that we've got a multi-user all using similar software, or maybe it's the same developer or contract of software, and then they have different versions, and maybe within those different versions there's a change in the way it's saving that file or saving that value, one using periods, one using commas, and it's ingesting into the same I don't know, server, I guess, or where you're reading it from. That's just a thought that I could have of where this mix would come in.
A lot of times what I would do there is read that column in as character, and then hopefully there's something else that can tell you whether you expect it to be period or comma, like maybe the country that the person is in or something like that. And then basically do a data transformation after you have it read in using the other column, or maybe like maybe you could just convert all commas to periods or all periods to commas and then parse it. But if it's got both in any one number, like if it has, 1000.2 like that, converting all commas to periods wouldn't work, because then you would have 1.000.2, and that's no good. Right. So, yeah, that's a hard problem. and
right. Now I was thinking maybe with this function you can just like when you load the file and then try to see if there's any problems in the files of this kind.
Right. Yeah. I mean, if nothing else, the problem function will tell you where it ran into weirdness, and knowing that can often be enough to fix it, especially if it's a small, sometimes like this, like I'll try to come up with some programmatic way to do it, and then there are 5 that are broken. So just go edit those 5 in the file, and then you don't have to worry about it anymore. So that's one thing to watch out for is it thousands that are weird, or is it just a handful? If it's just a handful, just fix it. You know. Yeah. Anyway.
Okay. So we have an example here of 1.23. So we'll use the pass underscore double, and it will return a numeric value. So if I want to change, this dot is the default. So if I want to change it, I'll use the local arguments and the local function. I'll say that I want the decimal underscore mark to be a comma instead of a dot, and it will return a numeric value as well. So what to know that read R default local is US centric, because the R is also US centric. That means that the documentation of base R is written in American English. An alternative approach would be to try and guess the defaults from your operating system. This might be hard to do well, and it makes the code fragile. The pass underscore number, we've said that this addresses the second problem, that what if a number is accompanied by another character? So what it does is that it will ignore the numeric character before and after the number. This is very useful, again, in currencies and percentages, but also works to extract numbers embedded in a text. So we can see this example, it will return a numeric value in ignoring any other character. We have the last problem with the different separator. So here we'll also use the pass number because we've said that it is flexible, and we can add the local function to ignore the grouping mark for the defaults. So for defaults, I am not really sure what is the default case for this, but you can see here it returns numbers without the, so I think the default is comma, yeah. So if we look at what is used in the other parts of Europe, this is for America, which is, we've said that it is US centric. So we expect that the default will be the comma, which is used in America. So for the other parts of the world, for example, where we have a dot that is used as a separator, we can change it using the group underscore mark, and you put whatever that you want. So this is a sin, and also we see that this has the quotes, and you can see it will return also numbers. So strings.
Thanks. This is very useful. We use this thing, the quote, and the dots are for decimals in Italy, in Europe, in Germany. So this is like, sorry about my dog.
Yeah, it's nice that it's it defaults. It has a default, but it's always the same default no matter where you are, so that you are it's not going to work differently if you're using code in a different place, and then past that you override it to be what you want it to be. So yeah, definitely useful.
Yeah, that's super interesting. So in Peru, at least, maybe not currently, but when I grew up here, millions were split by the quote, and then the rest of the separators were commas, all within the same number. So it's just interesting to think about, how all of these things are split and how it can cause problems when you're trying to read data in.
Yes, and yeah. And now we also have this the dots as a millions, and the commas as a million, and the dots stay with decimals. So we might have both of these things. Most of the times like this, and sometimes this. The old version was this with the quote. So sometimes it's tricky, because if you open it with, for example, Excel, it grabs you the things from your version of Excel. So if you are in Europe, if you are in America, whatever, you open the file and it transforms it automatically. So I don't understand why I found, for example, a mixture of dotted commas in. So that is like, I don't know how that happened, could have happened, but so maybe this is an issue that very tricky sometimes.
Okay, thank you for the contribution. And to know that in Africa we use comma. Oh, sorry, particularly Kenya. I don't know of other countries. Let me clarify that. So we have, for strings, like I've said, we have different ways of representing the same string. Hence we'll use the __ character. And this doesn't mean that it is as simple as we see. So we have to understand what is happening in how computers, represent strings. So we'll use the function the char to row to see the underlying interpretation of strings. So the example is for Hadley, and we see that it returns 48, 61, and so on. So let's understand the numbers. It's that these hexadecimal numbers represent a byte of information. So 48 would represent H, 61 will represent A, and we have got this 6C will represent L. So this is known as encoding. That is the mapping from the hexadecimal number to a character. And how R used is known as the American Standard Code for Information Interchange. For other languages, it gets more complicated. Like I've said, this is the standard one, which is supported everywhere and is as this, the UTF-8. Okay, so this can encode just every other character that is used by humans today and any other extra symbols such as emoji. So read R will use the encoding thing. This one everywhere. So it will assume that our data is UTF -8 encoded when we write and read it. So this is a good default, but it will fail for data that have been produced by older systems that don't understand this encoding. If you do so, it will print out strings that look weird, and at times these characters are messed up, and other times we will get complete gibberish. So for example, if we have this, it will return it will return this, the statement. If you have x2, it returns this. So we may not understand this, but if we want to fix the problem, we need to specify the encoding using the local. So we have seen that we have learned about 3 functions that we can do to alter the defaults using the local function. So here in case number 1, we have El Nino. So this is Latin 1. The encoding used was Latin 1, and it will print out what we see here. If we do the second vector that has been entered, this bunch of characters, that has been entered with this bunch of different letters here, the encoding is JIS, and we see that it shouldn't return this. In R it returns something else.
Yeah, it's funny that you got an encoding problem. Like, that's exactly demonstrating that encoding is painful. Whenever you have text and you have weird symbols showing up, it's an encoding problem. And it can happen if you copy paste into like something that makes it think that your encoding is something than what it was when you started, it is a very painful problem to deal with. Thankfully, more and more things are defaulting everything into UTF-8, and then you don't have to worry about it. But it is something I've had to deal with quite a lot. We have a lot of database fields that are set to Latin 1. And so it's not the same as UTF-8, and sometimes some character will come through broken, and you have to deal with that.
Okay, thank you. So how do we correct, how do we find the correct encoding? So first is that if the book said if you're lucky, it can be included in the data documentation. If you're not, readr will provide, will help us figure out what is the encoding, the correct encoding, and we use the function guess_encoding. This, please note, this is not a foolproof, but it works better upon having lots of text. However, it is a reasonable place to start. Okay, so we have our the first character of x1. We see that if you use the function guess_encoding, it will return a table with 2 rows and two columns with encoding and confidence. What does that mean? For x1, the El Nino statement was particularly bad for this year. If we do the guess_encoding, we want to check what encoding type that has been used. It returns these 2 columns, but I never understood what they mean. Would anyone help me?
So those are other encoding options, the ISO 8859 -1 and -9, and it's saying how sure is it that that is what the encoding is, and it's not very sure. The more text you feed it, the better it's going to do, probably. So if you know the short string, it's not going to be so sure. A long string, it'll be more sure. But yeah, it's still just guessing. So it's so much better if you can find out what it is. Like if you have information from the source of what is the encoding. It's so annoying that this is a thing, because UTF-8 solves it. If everyone would just use UTF-8, it would all be fine, but nope.
Okay, thank you.
Sorry, I didn't really answer that.
No, you have, like, I think I understand. Oh, sorry, there's another question.
Oh yeah, so on top of what John said, so it gets encoding, because he made mention like as more you put more data and it may predict accurately. So I'm not on top of at the back of the hood, is it like a kind of a machine learning classifier that's trying to do the prediction, or what? This encoding gets encoded. And does anybody have the idea?
Sorry, I'm taking a look at the code to see. It's not machine learning. It's much simpler than that. It's basically, it changes the encoding to different things and sees how much it changes, and then uses that to give a confidence on, oh, it's probably this.
Okay.
But it's much, you know, it's much more of an if-else kind of thing rather than machine learning.
So it's rule-based.
Yes. Or heuristic, as the word of the day.
Heuristic. Heuristic.
And I want to say that he mentioned heuristics once or twice in this chapter, and it's one of those words that I never encountered it, I don't think, before going into data science, and then it became a word that people use all the time. And so heuristic just means a set of rules, and people will throw it around and like, oh, I use a heuristic to figure this out. It means, you know, I use an if-else set of rules or some sort of tree. it's rather than like a statistical process.
Yeah.
Like machine learning. So heuristic. It's a word that once people know it, I think they really like to use it. It's a fun word. But
yeah, I like to use it also. Like in academic paper, we use heuristic rules to,
Yep.
yeah.
And then the other thing is, let's see how Zoom deals with encoding that. In theory, that is what Lucy was trying to show us with the shift GAIS. That it's it looks like it's not sure what language those characters are, but it's showing these special characters rather than the symbols that it originally printed as. So when you tell it the encoding. Yeah.
Okay.
Okay.
So all right. The first arguments.
Lucy, 1 second. Can I just interrupt on sort of a tangent? So what's the difference then between an algorithm and a heuristic? If an algorithm is also a set of rules.
That's a good question.
Yeah.
Because I'm just confused.
I think an algorithm is the wider term, that an algorithm can use statistical methods and it can have things that are more fuzzy, whereas a heuristic is just a set of rules. Like you're not doing any sort of
statistical.
Yeah. I don't, it's funny. I still don't really know that well. Let's see if I can get
Okay.
Oh, it's awful.
I'm frantically Google searching at the moment.
Yeah, because several of the Merriam-Webster definitions of heuristic have the word heuristic in them. So that's not good.
Yeah.
Trial and error methods. Huh. Okay. So yeah, I think it's more of a straight up like if else kind of thing. It tries this thing, and if that doesn't work, it tries the next thing. If that doesn't work, it tries the next thing. Is more what a heuristic is.
Yeah.
Versus, so that is a type of algorithm versus algorithm can be any set of rules.
Yeah. So
Okay.
Algorithm can be like a kind of well-defined set of instructions that you need to follow this to achieve this. But I think heuristic, you just try this and that and try to find a common way to achieve a particular stuff that may not necessarily be an algorithm with well-defined instructions, stuff like that.
I'll say that heuristics tend to be a lot more like brute force. Like,
yeah.
And I think that might be part of why the word is popular, because it makes it sound like you did something nice and fancy and cool, but really it's, well, I tried this and that didn't work. So I tried this other thing, that didn't work. So I tried this other thing and it worked. So I tried a heuristic.
I see. Okay. Thank you.
Yep.
That helps.
I was gonna say I just found a really awesome quote that I'd like to share, but this is off of Google and it's some is it Kiora, the place where everybody has their opinions of what should or shouldn't be. Anyway, I do like this quote. It says, an algorithm has a solution. An algorithm is math, so you can prove your solution. You know if it's right or wrong. In a heuristic, it's more of guesswork, just as John had mentioned. It said the key point about a heuristic is that there's no way of knowing when the solution you get is wrong. There's no way to prove it, right? There's no solution to it. You're just guessing. You're assuming that it's correct. Maybe that, John, I'm reinforcing your comments, or I think you had the good.
Yeah, it is funny. Like, it is one of those things. Now I'm going to go down this whole path because apparently it has a formal meaning in computer science, and that's part of why it comes in, I'm sure. But people don't use necessarily the computer science definition when they're talking about a heuristic. So, but yeah, that it's a set of rules that, it'll probably work. And that's part of it. Is I used a heuristic, so I'm pretty confident that I chose the right character encoding, but really you're just using something that hopefully we'll find the answer. And the same with what we were talking about with the columns in read CSV, that it uses a heuristic where it looks at the first 1,000 and it says, oh, looks like these are integers. But it's not necessarily right, because the 1,001st one might have been a non-integer. And if the heuristic were slightly different, it would have a different guess for what the columns were. Yeah.
So could you say one is more trial and error without a method behind it, whereas the other one would be a set of instructions for problem solving that provides an answer or something like that?
Yeah. Yeah. I think that's so. Sorry, I was reading that one of the things that they point out in the computer science definition is that it's for solving it quickly when something more formal would be too slow. So like you could set an algorithm up that would find the absolute correct answer for like the first 1,000 thing. Like in a 1,000,000 row data set, the true way to find the answer would be to look at all 1,000,000 rows and see what works. But good enough. Let's look at the first 1,000. That'll work. And so heuristic does have a little bit of a kind of hand wavy piece to it, that you're doing something that should be good enough.
Yeah.
But yeah, it's
a
word that, and I really do think that part of why it gets used so much is it makes it sound formal when it really is. I just did, I used a heuristic. Good enough. So.
Okay. I think I get it. Thank you.
Okay, so let's proceed. The first argument of the guess encoding is the path to the file, or it could be a row vector. And this is useful if strings are already in R. So we have been suggested, there's a suggested read here. If you get the slides, have a look at it. It's worth your read. So the other thing is factors. So we have learned that R uses factors to represent categorical variables that have a known set of possible values. So when we give a pass underscore factor function, a vector that is known, that has got known levels to generate, it will generate a warning whenever an expected value is present. So let's say this, we have a vector with fruits, with apple and banana. But now whatever we are passing here, so we pass, these are the known levels. However, we have got, this is banana now, and we specify the levels with the argument levels, the fruits. So we say that it will show us one passing failure, and it tells us the expected is the third, which is this banana, and this value is not in whatever is in the fruit vector. So we see a table that that gives us more information. So I tried passing the species column of the penguins data sets, and it returned such a table. We have been told, as John had suggested, if we experience problematic entries, it is often best to leave the vectors as characters. Now we work from there. So the other thing is about dates, the dates hyphen times and times. So we pick 3 passes depending on what we have. So we have a date, that is the number of days since 1970, January 1st. When we want a date and time, so this is, we're looking at the number of seconds since midnight, 1970, January 1st. And thirdly is time. That is the number of seconds since midnight. So these are the functions we do use. So when we use the pass underscore date time without any other additional argument, it tells us the type of encoding that is done. This is the ISO 8601 date time. And this is the international standard in which the components of bits have been organized from the biggest to the smallest. That is what I understood. So it will be, we have year, month, day, hour, minute, and second. So in this example, we have, if we do pass underscore date time, it will return the year. So it will return the dates and also the time and the time zone. But if we omit time, it will be set to midnight. As we've said, that if we don't include time, it will only show us the default, which is midnight. Okay, so this is the most important standard date time. If we work with dates and time frequently, there's a suggested read. Have a look at it, which is basically the Wikipedia page of the encoding of the dates. Another function now is the pass underscore dates, and here it expects a 4-digit year that is separated by either a hyphen or this is /, and then the month that also separates between the month and the day. We have got either hyphen or a /. If we look at this example where we have 2010-10-01, it will return such time. We have another pass function that is the pass underscore time. This will expect the inputs here to be hour, which is separated by a colon, minutes, which is optionally also separated by a colon between the minutes and the seconds. And we can also include AM and the PM specifier. So for this, we will use the package HMS and the function pass underscore time. It will return the time, the same as that. So base R do lack the great built-in class for time data. So that is why we have read about the HMS. If this default don't work with your data, you can supply your own date and time and build it up in the following pieces. So these are how you do it for the year, for the month as well. And there's also for the dates. I haven't learned this by heart, so I can't really mention all of them, but once you have the slides, please have a look at them. So one thing that we've been told to be aware of the abbreviations, because the EST is the Canadian time zone, which is different, meaning that it doesn't have the daylight savings time, and it is not the Eastern Standard Time. If we have got 9 digits, this is how you write. So what do we do in order to figure out the best correct formats? The best, it is to create fewer examples in character vector and tests with one of the passing functions. So we have, for example, we have got 01, this, so we see that this will return, we have month, /day, and then /year. So it will return, so we say that it starts from the highest, so it will return the year, the month, and the date. We can see some differences in this case. And another example is here, where we want percentage year, month, and date. So we see that it returns the year, this is the month, and this is the date. These the percentage small b and percentage capital B with the non-English month names. For this, we'll need to set a long argument to the local function. For you to know what the different dates, please check out this function, the dates underscore names underscore langs. And if you see, if your language isn't included, you can create your own using the date underscore name, so the date underscore names. I did run this in R. I was looking for our our local language, and I couldn't find it. Well, I wasn't really sure Kiswahili is KI or SW because it writes it as that.
Yeah, it's the, you can try with the SW, I think.
SW, okay.
Yeah, and another way to find all the languages available, you can just run date underscore names underscore langs without any arguments, and it will list all the languages available. Now, I'll write something down.
Okay, thank you. Okay, so we've said that we can create our own. This is for French. I cannot pronounce this, but it's 1st January 2015. And like I've said, with capital B, percentage capital B, it will return these dates. So the other section is, John, should we proceed? We have got 2 more, and now the exercises.
Sorry, I was stuck on mute. Yeah, let's go ahead and pause here, and we'll just pick this up next week for the second half of this chapter. This has been great. I really like how deep we've gotten into it. And, you know, like I was saying before we started, this is something that it's almost like I understand the philosophy of the book, but you need data to do anything. And so it's really nice to really get into how do you read in data. And so taking our time to go through it, I think is good. So yeah, let's just go ahead and pick up at 11.4 next week.
Sounds good. John, I can volunteer for chapter 12 then.
Okay, so you have 2 weeks to prep it.
Yes, perfect.
All right, excellent. All right, yeah, and I hope you're available next week, Lucy, to continue. If not, let me know, and we can go from there.
Yes, I am.
All right.
Perfect. Thank you so much, Lucy.
Yeah, thank you.
Thank you as well.
Bye.
Bye.